Exoplanets, or extrasolar planets, are planets that orbit stars outside our solar system. These celestial bodies have become one of the most exciting frontiers in modern astronomy, sparking curiosity about the vast universe and the possibility of extraterrestrial life. Discovering exoplanets, a technological marvel. The discovery of exoplanets began with an astonishing breakthrough in 1992 when two planets were found orbiting a pulsar named PSR B1257+12. This marked the start of a new era in astronomy, proving that planets exist beyond our solar system. These initial findings challenged traditional notions about planetary formation, as pulsars are remnants of massive stars that have undergone supernova explosions. Since that pivotal discovery, advancements in technology have dramatically transformed our ability to detect these distant worlds. Early methods were limited, relying on indirect evidence and incomplete data. However, the development of more sophisticated techniques has opened up the universe like never before. Each innovation has allowed scientists to uncover an extraordinary diversity of planets, revealing just how unique and varied planetary systems can be. The transit method is one of the most widely used techniques for detecting exoplanets. By observing a star's light dimming as a planet passes in front of it, astronomers can infer the planet's size, orbit, and even its atmospheric composition. This method has been instrumental in identifying thousands of exoplanets, particularly with the help of dedicated telescopes like Kepler. Its precision has allowed researchers to study planets in unprecedented detail. Another essential technique is the radial velocity method, which measures a star's slight wobble caused by the gravitational pull of orbiting planets. This method complements the transit technique by providing data on the planet's mass and orbit. Together, these approaches offer a comprehensive picture of planetary systems, advancing our understanding of their dynamics. The Kepler Space Telescope has been a game-changer in exoplanet discovery. Launched in 2009, it focused on a small patch of the sky, monitoring over 150,000 stars for signs of planets. Kepler's contributions have been unparalleled, with the identification of over 2,600 confirmed exoplanets. Its legacy continues to influence the design and mission goals of newer telescopes. Building on Kepler's success, the James Webb Space Telescope (JWST) has taken the search for exoplanets to the next level. Equipped with cutting-edge infrared capabilities, JWST can study planets' atmospheres in greater detail. This enables scientists to search for biosignatures, chemical markers that might indicate the presence of life. Its ability to detect faint light from distant stars and planets is revolutionizing our understanding of planetary systems. The sheer diversity of exoplanets discovered so far is astonishing. Some, like hot Jupiters, are massive gas giants that orbit incredibly close to their stars, while others, such as super-Earths, are rocky planets larger than Earth but smaller than Neptune. Each discovery challenges preconceived notions about how planets form and evolve, pushing the boundaries of current scientific theories. Instruments have evolved significantly since the early days of exoplanet research. Ground-based observatories like HARPS, High-Accuracy Radial Velocity Planet Searcher, have played a critical role in detecting planets. Meanwhile, space-based missions like TESS, Transiting Exoplanet Survey Satellite, continue to refine the precision and scope of exoplanet studies, ensuring that we uncover planets in a variety of stellar environments. As detection techniques improve, scientists are also focusing on characterizing exoplanets. Spectroscopic analysis allows researchers to break down the light coming from a planet's atmosphere, revealing its chemical composition. This has provided insights into the presence of water vapor, methane, and other compounds that might indicate habitability. The importance of technology cannot be overstated in the quest to discover exoplanets. Innovations in adaptive optics, data analysis, and telescope design have allowed astronomers to overcome significant challenges, such as the faintness of distant planets and the interference from their host stars. Each breakthrough has brought us closer to understanding the universe. Exoplanet exploration also benefits from international collaboration. Projects like the European Space Agency's Plato mission aim to study Earth-like planets in the habitable zone of their stars. Such missions reflect the global effort to answer fundamental questions about the potential for life beyond our solar system. The detection of exoplanets has profound implications for humanity. It not only expands our understanding of the cosmos but also addresses existential questions about our place in the universe. Discoveries like Kepler 452b, an Earth-like planet in the habitable zone, fuel the imagination and inspire new avenues of research. Despite the progress, challenges remain. The vast distances to these planets make direct imaging difficult, requiring advanced optics and computational models. Moreover, distinguishing between false positives and genuine signals demands rigorous data validation and cross-verification across multiple methods. Future missions promise to overcome these obstacles. Upcoming telescopes like LUVOIR Large Ultraviolet Optical Infrared Surveyor are being designed to directly image exoplanets and study their atmospheres in unprecedented detail. Such capabilities bring us closer to answering whether life exists beyond Earth. The journey of discovering exoplanets is still in its infancy, but the achievements so far have been nothing short of extraordinary. With each new discovery, we gain a deeper appreciation of the universe's complexity and the potential for life elsewhere. The story of exoplanet exploration is a testament to human curiosity and ingenuity, pushing the boundaries of what is possible. Diversity of exoplanets. Exoplanets exhibit a remarkable diversity that continues to surprise scientists and reshape our understanding of planetary systems. Each discovery reveals new characteristics, from their sizes and compositions to their unique orbital behaviors. This diversity challenges traditional models of planetary formation and highlights the vast possibilities within the universe. Hot Jupiters are among the most intriguing types of exoplanets. These massive gas giants orbit extremely close to their stars, often completing an orbit in just a few days. Their proximity to their stars results in scorching surface temperatures, often exceeding 1,000 degrees Celsius. Despite their size and heat, they provide valuable insights into how planets migrate from their formation zones. In contrast, super-Earths represent a class of rocky planets that are several times the size of Earth. These planets occupy a middle ground between Earth and gas giants like Neptune. Their varied compositions, ranging from dense, rocky surfaces to thick, gaseous envelopes, make them fascinating targets for studying planetary evolution and habitability. Another category is mini-Neptunes, which are smaller than Neptune but larger than Earth. These planets typically have thick atmospheres of hydrogen and helium and may possess solid cores. Their diversity in size and composition raises questions about their formation and potential habitability under unique conditions. Some exoplanets reside in the habitable zone, the region around a star where conditions might allow liquid water to exist. These planets are of particular interest because water is a fundamental ingredient for life as we know it. Discoveries like Kepler 452b, an Earth-sized planet in its star's habitable zone, ignite hope for finding life elsewhere in the universe. Rogue planets, which do not orbit any star, add another layer of diversity to the exoplanet catalog. These free-floating worlds may have formed in isolation or been ejected from their original planetary systems. Their existence challenges our understanding of planetary dynamics and raises questions about their internal heat sources. Some exoplanets exhibit eccentric orbits, deviating significantly from circular paths. These elliptical orbits can lead to extreme temperature variations, creating environments vastly different from those on Earth. Understanding such dynamics helps refine our models of planetary behavior and system stability. Binary star systems, where two stars orbit each other, often host planets with unique characteristics. These circumbinary planets orbit both stars, leading to complex gravitational interactions. The discovery of such systems expands our understanding of the variety of environments where planets can exist. Exoplanets also differ in their atmospheres. While some have thick, cloudy atmospheres that obscure their surfaces, others have clear skies that allow for detailed spectroscopic analysis. The study of these atmospheres reveals the presence of gases like water vapor, methane, and carbon dioxide, which are essential for understanding their climates and potential habitability. The surface conditions of exoplanets vary widely. Some may be covered in vast oceans, while others could be barren, rocky terrains or even molten lava worlds. The existence of icy worlds and desert-like planets further adds to the spectrum of planetary environments. Exoplanets also vary in their relationship to their host stars. Some are tidally locked, with one side perpetually facing their star while the other remains in darkness. This creates stark temperature differences and unique climate patterns, offering valuable insights into atmospheric circulation. Gas giants, like Jupiter, also display diversity among exoplanets. Some have rings, much like Saturn, while others exhibit strong magnetic fields that interact with their star's radiation. These characteristics help scientists compare exoplanets to the gas giants within our solar system. Planets with extreme density, often referred to as superdense exoplanets, challenge existing theories of planetary formation. These planets, with their compact size and high mass, suggest unique evolutionary paths and possible collisions during their development. The color of exoplanets is another intriguing aspect. Observations have revealed planets that appear blue, red, or even black, depending on their atmospheric composition and surface reflectivity. These colors offer clues about the chemical and physical processes shaping their environments. Exoplanets in multi-planet systems also exhibit intriguing interactions. Gravitational forces between planets can lead to resonance patterns, where their orbits synchronize in predictable ways. Studying these systems provides insights into the stability and evolution of planetary systems. The diversity of exoplanets reflects the complex processes that govern planetary formation and evolution. Each discovery expands our understanding of the cosmos and deepens the mystery of what lies beyond. From gas giants to rocky super-Earths, exoplanets are a testament to the boundless creativity of the universe. The search for extraterrestrial life. The question of whether life exists beyond Earth has fascinated humanity for centuries. With the discovery of exoplanets in the habitable zone, regions where conditions might support liquid water, this inquiry has gained scientific momentum. These planets provide the most promising environments for finding life as we know it. The habitable zone, often called the Goldilocks zone, is not too hot or too cold for liquid water to exist. Planets in this zone orbit at just the right distance from their stars, making them prime candidates for hosting life. Scientists focus on these worlds, hoping to uncover the conditions that foster biological activity. Spectroscopy has become a powerful tool in the search for extraterrestrial life. By studying the light from distant planets, scientists can determine the composition of their atmospheres. This method allows the detection of biosignatures, chemical markers such as oxygen, methane, and water vapor that might indicate biological processes. Oxygen is a key biosignature because it is often produced by photosynthesis, a process carried out by plants and microorganisms on Earth. However, its presence alone is not definitive proof of life, as oxygen can also form through non-biological processes. Understanding the context of an atmosphere is crucial for interpreting such findings. Methane is another important biosignature. On Earth, most methane is produced by living organisms, particularly microbes. If methane is detected alongside oxygen on an exoplanet, it could point to a biological origin, as these gases tend to react and neutralize each other over time. Water vapor is essential for life as we know it and is often a first indicator of a potentially habitable environment. The presence of liquid water increases the likelihood of life, as it serves as a medium for chemical reactions essential to biological processes. Its detection on exoplanets excites scientists about the possibilities of discovering living organisms. Beyond atmospheric analysis, the study of surface conditions plays a critical role. Planets with stable climates, tectonic activity, and magnetic fields are more likely to support life. These factors help regulate temperatures, recycle essential nutrients, and protect the planet from harmful cosmic radiation. The discovery of extremophiles on Earth, organisms that thrive in extreme conditions, has expanded the scope of what scientists consider habitable. From boiling hydrothermal vents to freezing Antarctic lakes, life has shown an incredible ability to adapt. This discovery suggests that life could exist in environments previously thought inhospitable. Exoplanets orbiting different types of stars offer unique challenges and opportunities. Planets around red dwarf stars, for instance, are often tidally locked, with one side perpetually facing the star. While this might create extreme conditions, it also opens up the possibility of life in more stable regions, such as the Terminator line between day and night. Technological advancements continue to push the boundaries of this search. Instruments like the James Webb Space Telescope and upcoming missions such as LUVOIR are equipped to detect even faint biosignatures. Their capabilities bring humanity closer to answering the age-old question of whether we are alone in the universe. The study of exomoons, moons orbiting exoplanets, is also gaining traction. Some scientists believe these moons could host life, especially if they have subsurface oceans like Europa or Enceladus in our solar system. The potential for diverse habitats beyond planets expands the possibilities for extraterrestrial life. SETI, the search for extraterrestrial intelligence, complements the search for biosignatures by looking for technological signs of alien civilizations. Radio signals, laser pulses, or even waste heat from advanced technologies could provide evidence of intelligent life elsewhere. Despite progress, the search for life beyond Earth is fraught with challenges. False positives, such as chemical signals that mimic biosignatures but arise from abiotic processes, must be carefully ruled out. Distinguishing between biological and non-biological origins requires robust models and cross-validation. Ethical considerations also come into play when searching for extraterrestrial life. The discovery of life, even microbial, raises questions about humanity's responsibility to protect these ecosystems. International protocols may need to be established for handling contact or contamination. The implications of discovering extraterrestrial life are profound. It would reshape humanity's understanding of its place in the cosmos and potentially answer one of the deepest existential questions. Whether simple microbes or advanced civilizations, the discovery of life elsewhere would mark a new chapter in human history. The search for extraterrestrial life goes beyond science. It is a quest to understand the universe and our connection to it. Each discovery, whether it finds life or rules out possibilities, brings us closer to unraveling the mysteries of existence. The journey is as transformative as the destination, reminding us of the boundless curiosity that defines humanity. Challenges in the future. Studying exoplanets remains one of the most ambitious and challenging endeavors in modern science. The sheer distances involved make direct observation incredibly difficult, as even the nearest exoplanets are light years away. These vast separations demand advanced technologies and innovative methods to gather meaningful data. The brightness of stars compared to the faint light of their orbiting planets poses another significant challenge. Stars often outshine planets by billions of times, making it difficult to isolate and study the planets themselves. Overcoming this requires specialized instruments, such as coronagraphs and star shades, which block out starlight to reveal the dim light of the planets. Atmospheric interference is another hurdle, particularly for ground-based telescopes. Earth's atmosphere distorts incoming light from distant stars, complicating observations. Adaptive optic systems have been developed to counteract this distortion, allowing ground-based telescopes to achieve higher resolution and clearer images. The limited resolution of even the most advanced telescopes presents challenges in directly imaging exoplanets. Current technology often relies on indirect methods like the transit or radial velocity techniques, which infer the presence of planets through their effects on stars rather than capturing direct images. False positives remain a persistent issue in exoplanet detection. Signals that mimic the effects of a planet, such as stellar activity or instrumental noise, must be rigorously analyzed to avoid misinterpretation. This requires extensive cross-validation with multiple observational methods and instruments. Despite these obstacles, the field is advancing rapidly thanks to missions like the European Space Agency's Plato mission. Plato aims to identify Earth-like planets in the habitable zones of their stars, focusing on finding worlds that could potentially support life. Its advanced design promises to refine our understanding of planetary systems. The James Webb Space Telescope, JWST, is another groundbreaking tool that has transformed exoplanet studies. Its ability to analyze atmospheric compositions and detect faint infrared signals allows scientists to search for biosignatures with unprecedented precision. JWST represents a significant leap forward in our ability to explore distant worlds. Upcoming missions such as the Nancy Grace Roman Space Telescope and LUVOIR are designed to push the boundaries of exoplanet exploration even further. These telescopes will focus on direct imaging and detailed characterization of exoplanetary systems, bringing us closer to identifying potentially habitable planets. The integration of artificial intelligence, AI, and machine learning has become a game-changer in analyzing vast amounts of data from exoplanet surveys. These technologies can identify patterns and anomalies that might indicate the presence of planets, accelerating discoveries and improving accuracy. Collaboration between space agencies, universities, and private institutions is driving innovation in the field. International efforts ensure the pooling of resources, expertise, and technology, enabling projects that might be unfeasible for a single organization to undertake. Public interest and funding play a vital role in the future of exoplanet research. The captivating prospect of finding alien life continues to inspire curiosity and support for scientific endeavors, ensuring that missions like TESS and future projects receive the resources they need. As detection methods improve, the focus is shifting toward characterizing the planets themselves. Understanding their atmospheres, surface conditions, and potential for hosting life will be crucial in assessing their habitability. Instruments capable of detecting water, organic molecules, and other biosignatures are at the forefront of this effort. The search for life beyond Earth is as much about our future as it is about science. Discovering even microbial life on another planet would fundamentally alter our understanding of biology, evolution, and the potential for life in the universe. Such discoveries could guide humanity's approach to exploring and protecting extraterrestrial environments. The challenges of studying exoplanets also inspire technological advancements that benefit other fields. Innovations in optics, AI, and remote sensing have applications in medicine, climate science, and more, showcasing the broader impact of this research on society. Ultimately, the search for exoplanets and the possibility of alien life remind us of humanity's boundless curiosity and drive to explore. Each discovery, whether it confirms life or deepens the mystery, expands our perspective of the cosmos and our place within it. The dream of discovering alien life is no longer confined to science fiction. It is a pursuit grounded in science, with the potential to transform our understanding of the universe.